Okay, so now we're at our last session. Because it's our last session, it's going to be very quick. So instead of talking more about like the rigorous definition, I'm going to talk about I'm going to give in some example and see how we kind of use this when we're studying economics. Because a lot of the times when you're doing economic researches, you actually don't know what's going on in the back door. You just run your equation using your computer and you get the answers. But still, you should know what is happening when you're running regression and you're getting p-values or you get a star. You should know what's happening, right? So I'm just going to talk about the process of doing that using like an example, okay? So statistics. Okay, why statistics? Firstly, why do we need statistics? Simple. In economics, we use data to see if our economic model understanding of the world holds. So, unless you're into like really hard micro or macro theory, unless you're like a very theory guy, there will be a very likely chance that you're going to have to use your data, okay, to answer some economic questions, and that's really something that happens often in economics. Well, but although this kind of is changing right nowadays, but it's mostly impossible to have all the data, okay? It's impossible the population data. Like, for example, let's say you want to know about like the wage of the people. You can't have the wage of every people living in South Korea, let alone be the world, okay? So, considering the fact, so we cannot have the full data. So, what we need is a theory that links the sample data to the whole population, right? Because sample data we can have a sample data of people's wages, but they do not mean the whole population data. So there are going to be some sort of measurement errors and some errors that comes due to the sampling. So we have to know how to use this and try to apply this to the whole population, right? And this process is usually called inferences, using the sample data, going to inference about the population data, all right? And this is a key concept in statistics. And I'm going to usually focus on the part where we can call like hypothesis testing. Because this is kind of basically what you're doing when you're running your regressions and you're getting like whether some value has a star or the p-value is like smaller than 0.05. You're gonna a lot of the time when you do your regression analysis in computers, you're gonna see your cases where your life gets really easier if the p-value is below 0.05. But if your p-value is 0.051, your life is going to get very miserable. And you're going to experience a lot of the situations. And you have to at least know why is that. Why are you happy as soon as your value goes below 0.05? But you become immediately miserable if it's over 0.05, like 0.051. Okay? We'll see why. And that's kind of related to hypothesis testing. So it's like basically a statistical method used to like make an inference or draw conclusions about the population based on the sample. So you're using the sample to take an inference about the population. And in economics, we want to get some values that we're interested in. For example, let's suppose that, we'll have an example here later on, but let me just like give an example here to follow up. Like for example, maybe you're like labor economist and you don't know about whether, never mind. Let's say you're like a very long time ago traditional empiric bio guy, like long time ago, like 50, 60, 1960s, and maybe you want to know about whether the concentration of the market leads to the profit of the market. For example, so if there's like, you want to know about if there's like only few companies in an industry, we all know that if it affects the profit of the market, or maybe if it affects the market prices, okay, you might be interested in these. All of these things are very old topics. And one of the ways to calculate whether the market is concentrated by few companies is that using factors like HHI. I think this was Hoppingdo, I forgot the name, Hoppingdo index, something like that. I forgot which H stands for, something like that. There's an index that kind of shows you that the market is concentrated, okay? Then you might want to see, like for example, very naively, you might want to do regression, which is you might have a markup. So y is the markup value, and you would regress this by some this. So basically, you want to know if this beta is not zero. So for example, if it's not zero, maybe if it's positive, this will tell you that the market becomes more concentrated, the market price goes up, right? And if it's minus, that means if the market is more concentrated, then the market price goes down. Although you cannot understand this in a causal sense, but let's just assume that you can, okay, for fun. And we're gonna see how this works out. Because like the problem is, if you have the whole data, it's okay, I guess. But if you because we only have sample data, right? The data points are all sample. So there's a possibility that this beta, in reality, maybe in the population data, this could be actually zero. But maybe because we have a sample, this might not be zero, okay? And this is problematic because that means that even if the world data is zero, you're getting non-zero answers, right? So you have to check that this is really robust with respect to the measurement errors and sampling errors. And that's where we kind of start using hypothesis.
So that's those kind of things, like economics, we want to check our values, okay? Like those kind of things are the values we want to check out, like the effect of something, right? And we want to see if this really matters, like if it's not zero. So this is where hypothesis testing comes into play. So what we do is that we make some hypotheses about the values. So we have a null hypothesis and alternate hypothesis, okay? So what this
Is that we assume first, we assume that the beta is going to be zero, okay? What this process really is doing is that we first assume that the beta is zero. The beta has no effect. So HHI will not have effect on the market price. We assume that. And we see if this will happen at a very low probability. And if it does that, then we can reject it. So for example, we can have a hypothesis first. Like, let's suppose that this is going to be zero. So we're going to say that HHI is not going to affect the market price. And later on, we can draw some sort of distribution of where that leads to. And for example, for that to happen, it will have to have a very small probability. Now, what this means is that this cannot happen, so we can reject it. Okay? And we're going to give an example for this. And that's where like a p-value comes out, basically.
You don't need to remember this much, but there are like different types of tests you can do, like two tail, one tail. I'm not going to talk too much about this. Okay, so we could think about what the computer is kind of doing for you when they're making a p-value star points. What they're doing is they're kind of doing the step-by-step procedure, which is firstly, we set up the null and alternate hypothesis. So we assume that HHI might affect the market price, right? So null hypothesis in this case is that the effect is null. So we're going to first assume that HHI has no effect on the market price, okay? And alternative prices would be like opposite, right? That HHI does indeed have some effect on the market price. That's the hypothesis we're setting, okay? And then we choose a significance level, and you might wonder what significance level is. That's the P part. So
remember I said like we're gonna assume this is zero, and we're gonna see how data must be chosen in order for this to work. And if it's in low probability, which means like there's very low probability of this happening, if we use the sample data we use, then we can say that this could be rejected. That's why, but we want to make a boundary. How much? Because data is always, they have like very tail distributed part. It's very likely that if you're very unlucky, data is like so off the charts, that's going to give you a very real result, okay? We're going to assume some kind of point where if we are over here, we're going to assume that this effect really happened. And if it's below here, it did not happen, right? So that's kind of like the significance level we can choose. And usually, we use the significance level to be 0.95, which is like a very strong point. Because what this means is that when you consider that most of the data to show that this happens, And if our data points are at the point where it's outside this boundary, like 0.05 percentage places, then we would assume that this effect indeed happens. Okay?
Then we're going to identify using the test statistics, and then using it, we can determine the distribution of the test statistics. That's what we were basically doing. We're using the distribution to kind of see how strong our data is, you know, to check if really the coefficient exists or not. And then using it, we can make a decision whether to adopt this or reject this, the hypothesis. So I have an example right here.
So basically, we have an example. So suppose a company claims their product lasts an average 40 hours. That's their claim, okay? And we will test if the average life is different from 40 hours, okay? They said it's going to last for average 40 hours. We will test if this is really true and if it's different from 40 hours. Like if it's different, it's using the sample. Because we can't test every product, right?
So we will set like hypothesis like this.
So basically, for our null hypothesis, we'll assume that the average is indeed 40 hours, okay? And our alternative hypothesis is mu is not 40. So if we adopt the hypothesis, we're just kind of saying that the average life of the product is going to be 40 hours, as the company said. Well, if we can reject this null hypothesis, and which means like we're rejecting this and adopting this, this basically means that the company's words are not true, that the average life is not 40 hours. Okay, we're checking that.
And we're choosing the alpha. 여기 알파를 0.05로 했네. Maybe I've been mistaken. Maybe it could be 0.05. It kind of always confuses me with the p-values. But basically, so we're setting the significant values. So basically, we're saying the significant value is like 0.05. So it's a very low probability. Okay. So we're setting like the boundary of which boundary that we'll use to whether adopt or reject the hypothesis. Okay. And using the sample mean and some known like population variances, I suppose, we can use some sort of z-test. Okay. So what the z-test tells us is that it kind of uses the data, the sample data, to see how our values are, with the location of our values in the whole overall distribution, and check if it's strong enough. Okay. And using it, well, suppose that we had like this variable, like for example,
like we calculated it, and you see like using the sample data, we got the average life as like 41.5, which kind of sounds like it's going to be like company's words seems to be kind of true. Like it seems like average 40 hours, right? But we still need to check the rigor streak. So we kind of for here we're going to assume that we have the number of samples 30. We assume like the variances, and we calculate the z-value. Okay. And you can kind of see this is similar to the standard normal distribution we mentioned before. So like we're kind of making a standard distribution, and if this is z, we're kind of seeing which part this value is going to go 1.74, okay? And see if it's far enough from the middle part of the distribution, okay?
all right. So basically, we have a data and we have the z-value, and we call this like critical z-value. Okay. So critical z-value for two-tail test is 1.96. What does this mean? Okay.
So basically, the good thing about standard normal distribution is that we can know exactly which points have like certain probability. What does this mean is that so basically, z-test allows us to draw some standard normal distribution like this. Let's say it's 0. And what that is telling us is that actually there's like a 1.96 and minus 1.96. Okay. Interestingly, in the standard value distribution, the probability inside here, if you sum it all up, it's 90. I forgot. It's 95, right? 95%. Okay. So if you have a z value, there's that here is 95%, and it's outside here, so here or here, you add them up, you get so this is 0.025. 0.025. You add them up, you get 0.05. Okay. So what this is telling us that if our test value is inside here, we cannot reject the hypothesis. We can kind of assume that the answer is our average life is similar to the average life which was set by the company, which is 40 hours, right? You can kind of see this because right now 1.74 is here. So in this case, we won't be able to reject the hypothesis, and we'll have to say there's no evidence that the average life of the product is different from 40 hours. And you can kind of see that this 1.74, this will increase as this increases, right? So for example, if you had a sample, instead of having average life 41.5, maybe you had like 100, okay? We got it and had 100 average hours, right? Then you get something like, z point will be like outside here, right? It should be like inside here, which cannot happen that much in probability unless it's actually maybe different from the average life. So what it's kind of saying is that if the sample value is big enough, you can kind of say that maybe the assumed condition where the hypothesis was that the average life hour is going to be 40 hours is not true, and it's going to reject the hypothesis, so our results are going to be below the P star, right? And similarly, so we're doing that. So similarly in comics, a lot of the cases, we have cases like similar like this. So what we do is that, remember the HHI index. So like, so we do regression. And a similar way we're doing it, we're doing is that as a researcher, we want this beta to be non-zero, right? Although, I mean, maybe you want to find a null effect, but most of the time you want this to be some sort of a non-zero value. But we have to check it, right? So what we're doing is that in a null hypothesis, we're assuming that beta is going to be 0. And we do this similarly, and we calculate the z-test, or t-test in this case, and then see if it's big enough. And if our value, if you run our computation, if the computer gives you like a p-value that's below the 0.05, what this basically means, the same thing here, is that the value is outside this range. So you can reject the hypothesis this, and we can say that beta is not going to be 0. Okay? However, if this p-value is bigger than 0.05, we're kind of saying that there's a possibility that beta can be 0. So we cannot say the beta coefficient is non-zero. That's why we're kind of doing it. And a lot of the cases in reality, in economic problems, you'll usually see this like more like graph 2. So basically, related to the confidence interval. So you might want to see some sort of effect, whether it happened. Let's say there was some sort of shock in like, there was some shock in 2010, 2011, 2012, and there's no shock before then. And what you can do is that you can plot the coefficients we saw before on the graph, and you can write it with a confidence interval, which kind of tells you that the range could be between them. So if this is like 0 value, you have some sort of like you have something like this. And ideally, what you want to have is like this. Basically, there's a point estimates, and you'll have some sort of a confidence interval. You go like this. Maybe like this. Like this. Okay? Although it's kind of weird. It should be like in the middle. Just bear with me. What this is kind of saying is that this interval is like what your value can be in population. So what we would want to have is that if there was a shock in 2010, and you want some sort of coefficient to have some effect, well, if you graph them, you have something like before 2010, your effect is like it contains 0, so your effect had no effect. But after 2010, your effect now, the interval is outside 0, right? Which means your effect is now non-zero. 이런 식으로 이제
하는 거죠. 그래서 잠시만 한국말로 말씀드리면
예를 들면 우리가 어떤 경제 만약에 어떤 셔업이 있을 때 그 셔업 효과 있을지 보는 건데 그러면 결국 개수나 어떤 코에피션트를 그리게 되는데 그 코에피션트의 값이 우리는 샘플을 가지고 하는 거니까 사실 이게 실제 퍼플레이션 데이터가 아닐 수 있잖아요. 그렇기 때문에 기본적으로 이거 이제 컴플레이트 인터벌식으로 해서 그리거나 이런 식이 많은데 이런 식으로 되는 거죠. 만약에 여러분이 가장 아이디어를 정한다면 이런 식으로 이제 처음 오기 전에는 여러분의 코에피션트가 0을 포함없으니까 0일 수 있다는 뜻이거든요. 그러니까 어펙트가 없었다고 봐야 되는데 없었다가 2010년부터는 이제 얘가 위로 올라가 버려요. 그래서 코에피션트가 0을 벗어나면서 그럼 이제 여러분의 코에피션트 어펙트 있었다 라고 말할 수 있는 거죠. 그런 식으로 많이 쓰이게 되고 여러분이 이제 뭐 P값을 구한다 할 때 흔히 다 이런 결국 과정이 있어요. P값이 작아지기 원하는 거는 P값이 작아서 별일 거야 여러분의 효과가 뭔가 파퓰리즘 상에서도 의미가 있다고 할 만큼 크다는 거죠. 그렇기 때문에
Yeah, any questions? Okay, so to wrap it up, the hypothesis testing is like way to provide a systematic way to test claims about a population parameter. So we want to say something about the population because we have a sample. So we are using the sample to talk about the population, okay? So properly setting up and interpreting tests is very crucial for making correct statistical decision making in a course in economics. So it's very important that you guys know about this basic understanding of statistical tests and take classes if you don't know it. But I just wanted to talk about a very brief definition and what you're doing when you're running your computers and your regressions, okay?